in the context of nuclear energy, the element that we're after is uranium. And uranium itself has a couple of different isotopes, and it's famously unstable. Remember, we talked about the term fission, right? So uranium will naturally undergo the process of fission, and one of the things that we've kind of figured out is that there's a way to concentrate and essentially accelerate that rate of fission and use that to generate power. As far as getting uranium, it turns out there's a lot of different minerals. We would use the term ore, minerals that contain uranium within their crystal structure, right? Uranium is not something like a native element that just exists on its own. It's contained in a variety of different minerals. Really, there's kind of the big five that we mine, and it's probably not worth our time going through, but going through and identifying each of them. But you can see here, generally they range in color from this kind of weird bright yellow to kind of greenish. Some are even more of a dark kind of I guess like a grass green. Others are a little more neon. And then there's also the majority of uranium comes from a specific mineral that's casually referred to as pitchblende, which is this kind of black stuff. So all of those are different minerals that contain uranium in their crystal structure. Meaning, if we want to get the uranium out of them, we would have to, take that mineral and essentially disassemble that mineral and pull the uranium out, which we can do, right? It's not incredibly difficult to do that. So with these kind of cool uranium-bearing minerals, those minerals do some interesting things, and it really is kind of related to oxidation state, meaning how much oxygen there is. So generally, if they're not oxidized, meaning they haven't reacted with oxygen, these minerals are soluble. And that means they dissolve with rainwater, right? Soluble just like sugar in your iced tea is soluble. Or if we wanted to think about a mineral, salt in your Bloody Mary, I guess. I was trying to think of a beverage you'd put salt in. Bloody Mary. Salt in that case is also soluble, right? It dissolves and then it becomes part of the fluid. So these minerals will essentially dissolve, and the uranium-bearing minerals are now part of the fluid. So that fluid is flowing as groundwater, right? So we've kind of talked about this concept before, water that's flowing through the pores, generally in places that have bedrock like sandstone, right? So we've also met this notion before, porous rocks. And so you can kind of imagine in your mind's eye, there's kind of uranium-bearing groundwater flowing through some sedimentary rocks like a sandstone, through the little pore spaces, and you talk about porosity and permeability, right? Those are two important things to think about. Inevitably, that groundwater is going to come in contact with an environment that we would describe as an oxidizing environment, a place where there's enough oxygen contained in the surrounding rocks. Remember that I said these minerals were soluble if they weren't oxidized. So as they're flowing through the groundwater, once they come in contact with this oxidation zone, they will recrystallize and then actually fill the pore spaces. And at that point, they're no longer soluble. So they're basically deposited in the pore spaces of rocks. But they're not a fluid at this point. Now they're mineral crystals that have started to crystallize and fill in those pore spaces. So it's different than when we were talking about oil and gas, right? It's not a fluid in there. Now, as it was contained in that water, some chemical reactions occurred, and those mineral crystals started to grow, and those pore spaces are now filled with uranium-bearing minerals. Geologically, if we kind of take a step back and think about where these rocks are occurring, initially these minerals occur in intrusive igneous environments, and then those rocks get exposed at the surface. This ends up as groundwater, and then out into some sandstone as groundwater, just to kind of walk through the few steps that we've already gone. Which, if you think about the geography or the geology of North America, out west We have a lot of fairly young, intrusive igneous rocks that are potentially contain these uranium-bearing minerals. And then also we have lots of sediments that are being kind of sloughed off as those mountains are being uplifted and eroded, kind of big aprons of sediment. So particularly down in the desert southwest, lots of sandstone exposed. That's a place where we have a lot of uranium exploration and uranium extraction. A few of these abandoned uranium mines kind of scattered throughout the desert southwest. Not particularly healthy places to go, but one of the things that we'll hopefully explore is that uranium, as it occurs naturally, decays really slowly. So you could have a piece of uranium ore, if you hold it in your hand, it wouldn't be disastrous. So there was a news story not too long ago about some uranium-bearing rocks that were stored at the Visitors Center at Grand Canyon National Park. Everyone lost their minds, like, oh my gosh, uranium, everyone's gonna die. And what people pointed out very quickly is that naturally occurring uranium decays very slowly and is generally safe to handle, so everyone was okay. But when we think about how uranium decays, we're going to have to get back into our discussion of isotopes. So we've got uranium-bearing minerals in the grains of a sandstone. We can go there, we can crush that rock up, and then we'll process it. We're going to get to that in a second. But before we start talking about processing the uranium, I wanted to kind of loop back and talk about isotopes of uranium. So there are actually a lot of isotopes of uranium, but there's some kind of big ones that we're going to be thinking about. And actually, you can see here on this chart. Remember, the second number is how many subatomic particles there are, right? So it gives you an idea of how many neutrons. So all of the uranium atoms have 92 protons. That's the definition of uranium. Atom with 92 protons in its nucleus, Carl, or uranium, right? We just give it a name. The name we've given it is uranium. But notice that we've got uranium-235. And if you kind of look over at the natural percentage, it's less than 1%, right? It's about 0.7%. We're going to come back to that number. That's why I'm introducing it now before we go through the rest of the processing. Uranium-238, which is kind of what you would call normal uranium, although it's not stable. It's unstable, but it's more stable than uranium-235. It decays at a slower rate. So you can see, a little bit over 99% of uranium that occurs is uranium-238. And then uranium-234 with a really, really, really small percentage. And like I said, there are even others that are smaller percentages, but we don't need necessarily to worry about that. What we're really going to focus on for the discussion is uranium-235 and uranium-238. And the other thing that I want you to start thinking about, but we're not quite there yet, is that each of those, the uranium-235 and the uranium-238, each of those have 92 protons in their nucleus. The rest of the number is how many neutrons there are. And the fact that that number is different means that those atoms are not the same size. They have different weights. So uranium-238 is very literally a heavier atom than uranium-235. That difference in mass is going to become key to this whole thing, right? So that's why and we'll talk through that a couple of different times here. So we're going to go through the process of taking our uranium ore and getting us closer to something that we can use as a nuclear fuel. And we're going to have to talk about a little bit of chemistry, obviously, but no chemistry prereq required. And the whole time we're going through this, I want you guys to kind of beat this into your brain. Although, again, the specific numbers are less important, but I want you to know that in naturally occurring uranium, uranium-235 is not even at 1%. Uranium-238 is basically the rest with a little bit of little bit of extra wiggle room that we can kind of ignore for now. So this becomes fundamental. Now, we talked about having these sand grains, and in the little pores in the sand grains, they were filled with these uranium-bearing minerals. And they said that those are soluble under certain conditions. They oxidized in the sandstone, and that's why they were left there. So we want to take those minerals out of the pore spaces and concentrate them, right? Because we just want a big pile of uranium, right? That's where we're headed. So a sandstone, thinking about the density of these minerals, right, as they're left here in the pore spaces, once a sandstone is in the realm of about 1% uranium bearing, at about 1%, that sandstone then becomes a viable ore. And again, you kind of have to keep the finances in mind, right? So at that point, you can make enough extracting those minerals to pay for the extraction of those minerals, if that makes sense. Numbers higher than this are really just kind of profitability, right? Once you're in higher grade ore, you're doing basically the same amount of work, but you're getting more final product, right? So at this point, 1% is pretty much the bottom, the floor of what we consider a mineable resource. And what we do is we take that sandstone and we crush it up and we put it in I don't know, you could kind of imagine it like a big coffee filter, and we pour acids over it, and some other specific chemicals. And what those chemicals do is first of all, they can't dissolve the sand, silica, right? Silica grains, the sandstone, that's chemically inert. It's not going to go anywhere, even in the presence of acids. It doesn't care, right? It's just yawns and gets back to doing what it's doing. But the uranium-bearing minerals, those ones that were present in the pore spaces of the rocks, they dissolve. And so if you were to imagine making coffee, right, you have the coffee grounds left behind, and then you have your wonderful black gold dripping out the bottom. That's kind of what we do with this uranium ore. Put it in a big vat, we mix in some acids, and you can see here, it creates this weird kind of uranium-bearing mineral sludge. And we take that sludge and we dry it. This is a terrible cartoon of what we've been talking about, but hopefully it gets you to understand kind of the big picture. So we would take that rock material, we put it in something like this, a coffee filter, pour a bunch of acid into there, stir it up, separate out the solids. We've kind of seen similar processes. And then eventually we get this sludge, right? This uranium-bearing mineral, this like mineral sludge, but it's essentially uranium. And so that then settles to the bottom, and it's actually kind of dried and put out on these conveyor belts, and it's this yellow powdery material, although it's kind of caked together. And that's actually what we call yellowcake uranium. So yellowcake uranium is often yellow. It's not always yellow. Sometimes it's tan, sometimes it's black. Depends on the ore that you were using. But this yellowcake uranium is what we're looking at here, right? So compositionally, it's just a fraction of uranium-235. It's mostly uranium-238. It's no more dangerous than holding a piece of uranium ore in your hand, but what we've started to see is that it's essentially concentrated uranium. It's pure uranium at this point. And this is really the last stage of uranium processing where things are what we would consider safe. Actually, I kind of clipped this off of the internet. Yellowcake uranium is the last thing you can buy, right? You can go online and buy some yellowcake. It's always in like terrorist movies. People are always doing deals of yellowcake, so it's a cool name. I guess it's kind of a cool name. But again, what we're going to see is yellowcake doesn't have a high enough percentage of uranium-235 to really create accelerated decay, because uranium-235 decays more quickly. but it's here in really, really, really low percentages, so it's safe. But actually the next step, and we're going to just start a new video with that one, is enrichment. And that's something that you hear about in the news from time to time. And at that point we can take these ingredients, this yellowcake uranium, and start to change these percentages and start to get to a higher percentage of uranium-235. Different percentages for different purposes. But we'll explore that in the next video. Alright, see you then.